Hello everyone and welcome back. Okay, so far we've described what happens inside a velocity, thermal, and concentration boundary layer. And we said that we have gradients that form near the surface on the surface, and essentially that these gradients control the friction, heat transfer, and mass transfer coefficients. And essentially, let's look at the friction here. For instance, you have the shear stress, and the shear stress is dependent on the velocity gradient evaluated at the surface. And so the higher the velocity gradient, then the higher the shear stress. And so the friction coefficient, which is proportional to the shear stress, would be impacted. And similarly, over here, you have the local heat transfer coefficient, which is this expression, and I showed you how we derived it. And so you could see it's dependent on the temperature gradient evaluated at the wall. And so the higher the gradient, the higher the heat transfer coefficient. And if we look at the local mass transfer coefficient, we see that the local mass transfer coefficient depends on the gradient of the concentration evaluated at the surface. And so far, we've been very descriptive in our understanding, and descriptive understanding alone cannot answer engineering questions such as how large is the wall shear stress, how much heat is transferred, how fast does a species dissolve or evaporate. And so to answer these questions, we must connect boundary level behavior to quantitative predictions. And so let me first tell you what my goal is in this section and then see what you want to do. Because I'm going to walk through a derivation and on a high level, and I want you to be able to understand where I'm going with this. So my goal in this section is simple. It's to show you why you need the Nusselt number to calculate the heat transfer coefficient and the Sherwood number to calculate the mass transfer coefficient. And now once this is understood, it becomes clear why convection, heat, and mass transfer coefficients are almost always reported in terms of these dimensionless numbers, in terms of Nusselt and Sherwood, especially in the scientific and engineering literature, and as we will see in the future sections. So if you're only interested in being able to apply these correlations, you may choose to skip this section. You can still use the Nusselt and Sherwood correlations that we're going to present later in the later chapters to calculate the heat and mass transfer coefficients without fully understanding where they come from. However, if you want to understand how and why these correlations work, then this section will walk you through the methodology and governing equations that really link these dimensionless numbers to the heat and mass transfer coefficients required to solve real engineering problems. However, if you want to understand how and why these correlations work, then this section is going to walk you through the methodology and governing equations that link these dimensionless numbers like the Nusselt and the Sherwood to the heat and mass transfer coefficients that you need to find in order to solve real engineering problems. So stay tuned.